Next up, Simon Hanmer will be speaking to you about one of the larger geologic features on Venus and some ideas about it.
Listening to planetary geologists, you sometimes get the impression that there's a bit of a competition going on among them to find the biggest whatever in the solar system. As I've discussed with you in past years, Mars leads the pack for the largest mountain, well, it's really a volcano, and the largest valley. And Jupiter's ice moon Callisto and our own moon are in competition with each other for the biggest impact feature. Now, in a recent paper published last year in the scientific magazine Geology, scientists think they've discovered the largest geological bump in the solar system. Next one, please, Chris. Now, when I say bump, the technical term for it is actually a tectonomagmatic feature, or a dome, but we'll come to that. Now, ever since the Magellan probe imaged the surface of Venus in the mid-1990s using radar to peer through the clouds of the thick Venusian atmosphere, planetary geologists have been able to make out a number of first-order topographical features. And using a combination of high-resolution images and gravity calculations, they've started to come up with some interesting interpretations about how some of these features actually formed. And in doing so, they're coming up with geological stories that show how some of these features actually formed either together or at least in rapid-fire sequence, such that they're probably genetically related to a common cause. And it's the cause I want to talk about. Now, the very obvious circular feature here in the southern hemisphere of Venus is called Artemis, and it was already identified in the first Magellan images of the mid-1990s. Now, geologists have been arguing about just how Artemis formed ever since its discovery. But the recent paper in Geology magazine suggests that it's actually just a pimple on a much larger geological feature. And if they're right, if they're correct, this would dramatically narrow the options for its origin. So let's take a look at the evidence in favor of what we can call loosely the greater Artemis, and what it tells us about the Venusian geological evolution. Now remember that, as I told you a number of years back, Venus has been completely resurfaced by planet-wide volcanic eruptions during the past billion years. There's some debate over exactly when the main resurfacing occurred. And some say that such volcanism might even be continuing to this day. So my point is that by the standards of our 4.5 billion year old solar system, the geological features of the greater Artemis that we'll look at here are relatively young. And it shouldn't be a surprise, the greater Artemis will actually be something like this, but I'll show you. Next one, please, Chris. Now, this is about as natural, in inverted commas, a view of Venus as one can get. This is a radar image. The radar can penetrate the cloud, and it can see topography in some pretty good detail. The white features, here, and then across here as well, those are areas of very strong radar reflection, and it's due to a surface coating of fool's gold. It's not gold. More technically, it's known as iron sulfide or pyrite. Now, notice how this forms a broad east-west band with large dense patches to the west here and up here to the north, and then this squiggly stuff over there. And there's this very obvious circular feature round about the midpoint here. That, of course, is Artemis. That gives us some kind of orientation. By the way, Artemis is about 2,100 kilometers across. Next one, please, Chris. Now, this is a false color image of Venus. In other words, it's been photoshopped. And it picks out rough differences in geology. The tan and white areas here are quite distinct from the blue and green areas. And if you get your bearings, here's Artemis there. And we can see the same patches to the west and the north that we saw on the previous image. Now keep these in mind, these large patches, as we'll come back to them throughout the talk. Next one, please, Chris. And this is a different false color image of Venus, this time picking out rough differences in topography. Yellowish colors are high ground, so up here, here, and then across to there. There, of course, is Artemis. And the greenish colors are generally low ground. Now, notice that Artemis actually lies on the south side of a band here of relatively high ground. and with those two patches to the north and to the west. And then here's that squiggly stuff leading over to yet another patch further over. And those are the squiggly strands I'll come back to in a moment. Next one, please, Chris. So let's put all these features together now on a single radar image. And if we do that, we can see here's the circular feature Artemis. And it's part, really, of a larger highland region, which is all of this, which is known as Aphrodite Terra. And the word terra here just means ground. Aphrodite Terra is made up of Ovda, Thetis, and Atla Regio. And Regio here just means highland. But you can see these are the patches that we saw on the previous false color images. Now, Ovda and Thetis are neighbors, obviously. And Atla here is linked to them through this corridor here of rather complex-looking rift valleys, which are referred to here as the Diana Dali, the two names, the Diana Dali Chasmata. And Chasmata just means chasms, in other words, valleys. That's what it means. So remember, given that Artemis is over 2,000 kilometers long, you can work out for yourselves practically how long that is. Next one, please, Chris. So what exactly is Artemis? Well, this map here shows Artemis down there. There's the two patches of high ground. There's Ovda Regio and there's Thetis. And in fact, what it is, it's a round feature, and it's called the feature itself is referred to as Artemis Corona. No, it's not named after the Mexican beer. It looks like a moat, and that moat that surrounds it is called Artemis Chasma. Yet again, that word for valley. Next one, please, Chris. Now here's a more photographic close-up of Artemis. This obviously is Artemis itself. These round corona features are characteristic of Venus, but this one is by far the largest and the most spectacular. The moat-like feature that surrounds it is a circular valley. It's 25 kilometers to 100 kilometers wide, depending on where you are, by about 1 to 2 kilometers deep. There are lots of theories as to how it might have formed, and these range from an impact feature to the product of magma welling up from deep inside the planet. And some geologists have even suggested that it formed by plate tectonic processes, but this does not stand up very well to scrutiny. However, all of these hypotheses are hampered by the fact that such corona features do not occur on the Earth. They're unique to Venus, so they're difficult to test, even by simple comparison to knowledge of our own planet. There are round structures on the Earth bounded by circular depressions, there's no doubt, but there's nothing quite like this, and certainly not formed on the surface like this was, and certainly not of this size. Now, at the beginning of the talk, I mentioned that if Artemis really is part of something much bigger, geologically speaking, then this might have repercussions for theories about its origins. So let's now pull back and let's look at the really big picture of this part of Venus. Next one, thanks, Chris. There we go. Now, the paper in Geology magazine proposes that everything we've looked at so far is, in fact, a part of an even larger geological feature that we can refer to colloquially as the Greater Artemis. So there's Artemis itself, and we're going to be talking about a feature of this kind of size. Now, the white circle indicates the approximate outer limit of Greater Artemis. That's about 13,000 kilometers across. You can see that this coincides with the approximate outer limits of a set of red concentric lines. You see them here? And then they're really very pronounced down here too. Now, what exactly are these things? They're referred to as wrinkle ridges, but it's not the same thing as the wrinkle ridges you hear about on the moon. Let's look at some examples from north of Ovda Regio, and Ovda Regio is this one here. Remember, there's Ovda, there's Thetis, and there, over here, is Atla Regio. Okay, next one, please, Chris. Now, what I want you to focus on is this over here. See how there's this hairpin bend? Oh, sorry, there's a hairpin bend there and a hairpin bend there. Now, a geologist will immediately recognize these hairpin bends as in layering, in geological layering, as folding. And folding of a layer implies that the layer was shortened, more or less, perpendicular to the traces of the fold. In other words, it was squeezed by being pushed along a line like this. However, not all folding on Venus is as easy to see and identify and to decipher. Next one, please. Much of it looks like this. When the shortening gets locally intense, the hairpin bends disappear. And what you end up with is a series of simple stripes without the actual bends. But to a structural geologist, they clearly represent very tight folding of volcanic layers close to the Venusian surface. Next one, please. Now, in addition to the concentric folds, you can clearly see a set of radial lines. You can see them very well down here. And they're in black here, by the way. And then here they are again, coming out like this, these radial lines. These span a circular area about 12,000 kilometers in diameter. And they all seem to point inwards towards Artemis. Now, again, a geologist would immediately recognize these as a giant swarm of radial dikes, a feature that's not uncommon on Earth, but is rarely this big. So what is a dike swarm, and what does it imply? Next one, please, Chris. Dike swarms are, in reality, swarms of cracks in a planet's crust that fill with molten magma under enormous pressure. That magma is trying to rise up towards the planetary surface. Some terrestrial examples are shown on the right-hand side. Here's a nice big Canadian one, by the way, coming from the Canadian Arctic right the way down to Lake Superior. And the block diagram over here on the left-hand side, this indicates that such swarms usually form as the planetary crust is being extended. It has to be extended to accommodate the injection of the liquid magma. That's the complete opposite of the shortening implied by those concentric folds. Next one, please, Chris. Now look at the main band of highlands down through here, going from Ovda Regio out to Atla Regio. And notice the speckle pattern that's drawn through here. It's in a sort of a clear band, an east-west band, if you will. And it includes here the rifts of what I referred to as the Diana and Dali Chasmata system. Next one, please, Chris. This is a photographic close-up of the Chasmata system. From here to here, there's Artemis, by the way. This picture is 7,500 kilometers across. Now notice how intricate the Chasmata system is, all these various strands. Each of these radar-bright strands is a rift valley, and rifts, as in our own Ottawa Valley, indicate extension of the planetary crust at a high angle to the valley trend. In other words, there's the valley trend, and you've extended in that direction there. Now let's go back to the big picture and put these rifts into context. Next one, please, Chris. See how the speckled band here cuts right across Ovda and Thetis Regio, cuts right across like this and just keeps on going. Until you come to Atla Regio, right there. And then something rather remarkable happens. It actually divides into 1, 2, 3 branches. Geologists instantly recognize this. Oh, by the way, I should have mentioned that the branches come together dead in the dead center of Atla Regio. And geologists instantly recognize that this is what we refer to as a triple junction that forms as the planetary crust is stretched and split above a rising dome. If a dome is rising like this, then the crust above it, the skin above it, must stretch. You've gone from this to this. In other words, in the case of Atla Regio over here, that rifting, represented by the speckle pattern, is related to the formation of Atla Regio itself as a dome. While in the case of Ovda and Thetis Regio over here, the rifting, indicated by this speckle pattern through here, ignores the highlands completely. It just cuts right across them. And what that tells us then is that the rifting here is younger than the formation of these two highlands. Next slide, please, Chris. All right, I hope you're beginning to see where I'm going with this. We now have the outline of the geological story that evolves through time. This is a Mickey Mouse sequence of what I'm going to be showing you. And so it reads from here at the oldest to this at the youngest. The greater Artemis feature appears to be a gigantic dome in the Venusian crust that formed above a gigantic plume of hot material that rose from deep in the planetary interior. So here's, in Mickey Mouse form, there's the plume coming up, and the dome is going to form here. As it did so, smaller domes began to form above the plume in the early part of the story, giving rise to Ovda and Thetis Regio. Now, that would be somewhere around about there. It's slightly out of sequence. I would have preferred it to be drawn there, but unfortunately I'd grabbed this diagram here. Anyway. As the rising plume grew, a progressively larger volume of the Venusian crust was induced to participate in the dome above the plume. And you can see this represented here. The plume starts to form a dome here, and the dome then grows and grows and grows, getting larger and larger, involving more and more crust. As that dome grows, so the outer crust of the dome begins to stretch and break, and it forms a giant radial dike swarm centered around the Artemis corona. So that's what these things here represent. This is the radial fractures as this dome is growing larger and larger and larger, and they're focused on that point there, which would represent Artemis itself, if you will. At the same time, around the periphery of the giant dome, the planetary crust begins to buckle because it's sliding off the topography that's being built by this rising dome. And that's what's represented here by these red concentric lines. And it forms these concentric folds that as they become progressively tighter, they're transformed into stripes, which are then called wrinkle ridges. Now, eventually, the top of the dome rises so much that it splits along an east-west axis, which isn't directly represented here, but it would be like this, there, or there. And it splits along an east-west axis, except in the east, which would be represented by this here, this here, this here, where you've got a triple junction which forms over a new, even younger dome, which we now see as Atla Regio. And that would therefore be one of the youngest features in the evolving Greater Artemis structure. So now that you've got the entire Greater Artemis story, let's go back to the big map of Venus and briefly summarize how that story works. So here we are. We've got a structure this large, which is going to form as this plume comes up through the mantle of Venus. It's coming up around about there. As it comes up, it domes the crust on this kind of scale. The crust begins to split along these radial dikes. As the topography grows, so the outer layer of the crust begins to slide off away from the rising center of the dome and forms these folds around the outside. Parasitic, if you will, like pimples growing on the larger dome, you initially get Ovda Regio and Thetis Regio begin to form as smaller domes on the big dome. And then the big dome itself begins to split along the Diana-Dali chasmata. As that rifting is occurring, so over in the east, you now get a third, even younger dome, the Atla Regio, and the rifting here now responds directly to the fact that a dome is rising up under the rift. So the rifting here is the same age as the dome here, whereas the rifting is younger than the doming here. So there's your overall story. Finally, what do we know about what caused the Greater Artemis feature to form? At 13,000 kilometers, it is the biggest dome of its kind, or the biggest dome full stop, anywhere in the solar system. There is nothing of this kind of size. Frankly, they don't know too much. There's some speculation that the trigger could have been a major impact from outside that might have catalyzed the upwelling in the planetary interior, but we'll have to wait and see if that idea actually has any legs. What we do know, as I say, is there's nothing like it anywhere else in the solar system. Thanks for listening, and happy year of the solar system.